you know, Chebyshev's name appears everywhere in approximation theory for sure. Other areas of mathematics. Actually, he was quite, as I read, it was quite broad, not only in mathematics, but he jumped outside of mathematics and worked on practical problems, something that none of us do anymore, where mathematicians used to do that. So that to me was significant. I was going to go and see and count how many papers I had that mentioned his name. I'm sure it's 40, 50 papers because he's all over the place. And I had one paper with his name in the title. So I know that. All right. So what I want to talk about today, and I think this is a subject that is currently very active and getting a lot of notoriety, and that is how do we learn from data? So I view this core problem as the following, that we're given some data about some unknown function f. It's unknown to us. All we see is the data about f. And we want to use this data to predict the behavior of f away from the data. So we want to create something I'll call f hat, which is an approximation to f, right? Well, this example is definitely not in the ballpark of what I'm going to talk about, but it's something that you can keep in mind as sort of a motivation for what I'm doing. Suppose you had a function on 0, 1, and you observe some values of f at some points, xi. You receive the values of f at xi. The problem would be to predict what f is at other points, x, in the interval 0, 1, away from the data. You can use this for intuition as I march through this talk. Now, really, in modern applications, one of the important points is that typically our applications, the function is defined on a domain in Rn. I think later I sometimes use little d to denote this ambient space dimension. And capital N is very, very large. Problems in imaging, capital N is 1,000 or 2,000. So this will be a distinction that we're going to have to draw later. Now, when you look at this problem, there are both deterministic and stochastic settings for this problem. I'm going to live in the deterministic world until the very end. At the end of the talk, I'll say something about the stochastic setting. In the stochastic setting, you typically assume the xi's are chosen at random and the data is polluted by some noise. But I want to avoid this for a while. So the idea, you start thinking about this, and you wonder, one of the things people are complaining about is this modern theory of deep learning. We don't have any mathematics to really justify or even understand what they're doing in deep learning. And of course, that's ultimately a goal of mine, would be to try to add something to our understanding of that area. But I think it's best if we move slowly. I mean, when you talk to people working in deep learning, their problem is embedded with so many aspects to the problem, how they do the deep learning, neural nets, gradient descent, stochastic gradient descent, and mixes it all together in one big soup. It's kind of hard to sort out the various aspects of this problem. So I want to march through this in a very slow pedestrian way to understand what we're trying to do in this area. Okay, so let's first take the functional analytic approach. If you're a functional analyst and you're given this problem, and the first thing you would say to the person, well, tell me how I'm going to be judged in the end when I give you my F hat. How are you going to measure how successful I have been at constructing an approximation to F? And that would usually be in some norm, right? We would measure how the original function F and the animal we create, F hat, how far are they apart in some norm? In my talk, I'm going to, so you measure the error by this difference. And in my talk, I'm going to stick with Hilbert space norm for most of the talk, but you can do this in Banach spaces as well. So the other thing you would immediately ask for if you were given this problem by someone, and you would say, well, wait a minute, I can't do anything unless you tell me more about the function f. If you tell me nothing about f, it could be anything away from the data. So to have any kind of a mathematical theory, we need to have some knowledge about what f, something in addition to the data about f. We call this model class information, that f is in some compact set of functions. This extra information may be in the form of smoothness or knowing it solves the differential equation or some other information. And this is going to be important throughout the talk. Okay, and now I view the data that were given as linear functionals applied to f. So this is linear information. This matches, I think, almost every application. So my problem is I have this f, and I get to see these numbers, wj, which are linear functionals applied to f. In most applications of deep learning, these are function values of f, but at this stage, we don't care. There is a little wrinkle that in a Hilbert space in general, you don't have function values, which can be circumvented in several ways, one of which is to assume you have a reproducing kernel Hilbert space, but we'll talk about this later. There are other ways where you really need to know that these linear functionals are defined for functions in your model class only. That's enough. Okay, so if this is the setting of my problem, what do I know about f? I know that f is in a set k sub w. W is these numbers, these m measurement numbers. So what is kw? Kw is the set of f to satisfy the data. The f is in the model class. That's what kw is. That's the totality of information I have about f. Okay, so that is the problem. We're given a function f and kw, and we want to recover f by some approximation or numerical method. All right, so there's actually an optimal solution to this problem, which is called the Chebyshev ball. And it's easiest to explain with a graphic here. So think of this blue region as the set kw, right? It's a set in your Hilbert space. So this is your blue region. And all you would know about the function f you're trying to recover is that it's in this blue region. So if you look to approximate f, what's the best you can do? The best you can do is take the smallest ball that contains kw, contains this blue region, and take as the approximation the center of this ball. That would be the best you could approximate, and the error you would receive is the radius of this ball. So this Chebyshev ball gives you a theoretical description of the best algorithm, the best performance you can do in recovery. Let's make some, it's going to be very hard to find this Chebyshev ball. I mean, that's going to be our numerical problem. How do we find this Chebyshev ball? How do we find a center or something close to the center? How do we estimate the radius? Issues like that. But theoretically, this is the problem that we have to entertain. And notice that if I found any point in the blue region or any point in the ball, that would already be quite an accomplishment and would give me an algorithm that is within a constant 2 of being optimal. And one would be satisfied with that numerically if you could do that. Okay, so that's more or less what this slide here has said. Okay, so I want to get into this a little bit deeper into the geometry, the Hilbert space geometry of this problem. And To do so, let's take our measurements. We know that these are linear functionals, so they can be represented via the Riesz representation theorem as the inner product with some fixed functions. I call them omega j, right? So if you were doing point evaluation, your omega j's would be delta functions, but I'm in a general setting. And if I look at the span of these, so I'm in the setting where I assume the omega j's are in this Hilbert space because I've assumed that the data comes from measurement functionals defined on the Hilbert space. So I can form this subspace W contained in H, which is the span of all these omega j's, right? These are the functions used to generate the data. Okay, from the data information, you can always compute the projection of F onto the space W, and I will call that my data, little w. And I may have been given it in a different form, but I can always make this step and view little w as the projection of F onto capital W. By the way, you know, when you do these Zoom talks, you have no idea whether people are following you or have even left the room. But if you have a question, I'm willing to interrupt and take a question. Volodya maybe can monitor this, but because I don't want to lose anybody during the talk. Okay, so back to the thing. So what we really know about F, the data, tells us the projection of F onto this space W. What we don't know is what is the projection of F onto the orthogonal complement of W, right? Onto W perp. And that's the whole numerical problem. How are we going to find a good component for F onto the orthogonal complement? This is away from the data. Okay, and to do that, this is where we have to invoke that we know that F is in K. If we didn't know F is in K, we could say nothing about this projection onto the orthogonal complement. So this is the view to take. And I have a little graphic for this. So think of K, remember, was now K is this blue set. And if, because the graphic is in 3D, everything looks kind of simple, but from the data W, I would know this line segment, which is all the functions that satisfy the data that live in K, right? So this would be KW, this black line segment. And what we'd like to do is find a point or the center of this segment or any point on this line segment. And that's what we would use if we could find it as the component of F in the perp direction. And that is how we would build our numerical algorithm. So this is a very simple geometry, and you should keep this in mind as we proceed. Okay, so let's talk about what people do and how we could perform. So, you know, if you were teaching a course and some student came to you with data and asked you how he should learn the function from data, you would probably recommend to him something like least squares algorithm. So I want to say a few words about least squares. Bottom line is least squares as it stands will not solve our problem. Let's make clear that it won't solve our problem. So what does least squares do? You're given your data, and what you typically do in least squares is you find some, let's say at the beginning, a linear space of some dimension that you're going to use in order to approximate your function F. And what you do is you say, oh, I'll look at in this linear space and I'll try to find a function S, right, in this linear space that matches my data as well as I can. If the dimension n is less than m, you would not have an exact match of the data. You would have an approximate match. If n equals m, you could match the data exactly, typically, right? you would be able to match it exactly. It's like interpolation of the data by an element from this linear space sigma. If you choose an n bigger than m, now all of a sudden you enter a very shaky world, because this is the over-parameterized case, and you don't have a unique solution. And so you say, well, what the heck, which solution am I going to pick from this collection of possible solutions? Now, I think most people are used to the case where n is less than m, because they were motivated by statistics. And statistics, people said, oh, my measurements are noisy, and I don't want to directly fit the measurements exactly. That we call overlearning, right? So we don't want to do that. So we take a space of dimension less than m. But in fact, in the deep learning business, they take sigma. First of all, not as a linear space, it's going to be a nonlinear manifold. And secondly, they're going to take it where n is much larger than the number of data that you're given. So the over-parameterized case. So you can see that this is opening some doors at, well, a shaky world that we really don't understand what to do. Now, the motivation, or you might say, well, how should I choose sigma? Well, you would choose sigma so that it approximates the elements of K well, right? Because you know that F is in K. So if you had, for example, a Sobolev ball or something, you might use polynomials or splines or wavelets. But you would choose an approximation space, sigma, that matches your knowledge of what the model class is, right? That's sort of the idea behind how you would choose sigma. Now, I say to you, actually, least squares does not do very well at all. And you may say, well, you know, what can I say about least squares? Sorry for the jump. Actually, when you look in textbooks about least squares and numerical analysis, very seldom do you see a numerical estimate for the performance of least squares. But there is one, and here's the form it takes. It says that least squares will give you an error of some constant mu times the distance of f to sigma. Well, the distance f to sigma, you like that because you chose sigma so that this distance is small. But what is this constant mu? This constant mu pollutes the whole setting, because mu sort of represents how the data sits relative to sigma. I mean, here's a concrete description of what mu looks like. The bottom line is that mu is always bigger than 1 and could be huge. Mu could be huge. And this is what prevents us from saying that this least squares, as it now stands, gives us something close to a point in the Chebyshev ball. This f hat, I cannot prove is close to some element from the Chebyshev ball, and I can't prove that is close to an optimal solution. Why I can't do that is because you know, I can't relate to sigma, and this mu is possibly destroying me. In fact, if you look, whenever n is bigger than m, this mu will be infinite, which means in that least square sense. And you can see that because I haven't specified in the least squares anything about k. Once I began with k, I used k to find the subspace sigma to use, but then I forgot k. And I said, no, I don't employ k any longer. I'll just do this least squares fit from the, notice k doesn't appear here. You're just looking at all guys in sigma that match the data. And there will be guys in sigma that match the data that are outside of, I mean, very far away from F. All right, so what's the bottom line? Least squares does not meet our goal. All right, that's first thing. All right, is there a a fix to this? And the answer is, yeah, sort of. There's a fix. The fix is to utilize K in a more substantial way. And this is called penalized least squares or regularization. You're probably familiar with Tikhonov regularization, right? Not our Tikhonov, not our Sergey, but some, we don't want to give him too much credit, some other Tikhonov. Okay. So what is penalized least squares? Well, let's first do an idealized setting where we said, okay, let's solve this least squares problem, which is not numerically possible, but I want to think about theoretically. I'll look over all elements of my Hilbert space, and I'll ask that I'll look for a function G that matches my data well. I want to minimize this, but with a penalty that says I don't want the norm of G. Oh, I haven't made a transition here. Sorry, I have to back up for 1 minute. I'm assuming now that K is the unit ball of some space Y, which is a subspace of H. I want this for motivation purposes. We'll later move away from that assumption. But if K is a unit ball, for example, you can think that your Hilbert space is L2, and you have a unit ball of a Sobolev space or a Besov space that's embedded into L2, and that's what K is, okay? So I want that only to illustrate this particular slide. We'll later move away from that assumption. But if we have this, then we would know that K, that F was in the space Y and had norm 1, right? So we would look to fit our data with functions from Y, which have a controlled norm. So if we look at this minimization problem with this parameter lambda, which is similar to Tikhonov regularization or lasso algorithms and the like, you can prove that this solution to this problem actually solves your original problem if you could implement this numerically. Namely, as you drive lambda towards 0, if lambda is small enough, the minimizer of this problem will actually be close to the Chebyshev ball, and you will get a near optimal algorithm, okay? This is easy to prove, and you can probably do it in your head as I am talking. Well, I said this is not possible to implement numerically because I'm searching over all of H, right? You can't search over all of H. Therein lies the problem. We want to discretize H. We have to go to a discrete formulation, either through a finite dimensional subspace or some discretization technique, and try to implement the analog of this. And this may explain why in deep learning, they choose over-parameterization, right? Because if I restricted n to be less than m, I couldn't guarantee that I'm close to this kind of a minimization. But if I'm in the case where n could be very, very large, right, the dimensions of the space, then I can sort of see that I'm getting close to emulating this minimization over all of H. Okay, so bottom line is theoretically penalized least squares will do the job, but it's not possible to implement it numerically. So we have to go through more. Let's see, I think I will skip this. This is sort of the description of precisely what do I mean by penalized. Oh, okay, maybe I have to say some words about this. Because in practice, we replace H by a subspace, sigma, maybe a finite dimensional linear space, or maybe a nonlinear manifold of finite dimension. And we solve this minimization problem over sigma, which now you can say, well, maybe I can do this numerically, right? To solve this penalized least squared over a subspace sigma. then the question is, have you solved the problem? Well, it'll depend on how good sigma is at approximating your model class K, but it also depends on how sigma sits relative to the data. So I just want to mention that there is a quantitative theorem that tells you how well you do, and it requires something about these sets KW, that as W changes, the KW do not change too much. And that is a critical point in this theory, but I don't want to get into it too much. So what you should get from this slide and from what I've said so far is, yes, potentially we could solve our minimization, our original goal of having an optimal or near optimal algorithm by going to some discrete set sigma and solving a penalized least squares, but there are a few wrinkles to making this realizable. Okay, so let's now go to deep learning, what people do in deep learning. And then I want to see, well, are they coming close to doing this best or near best algorithm? And deep learning has gotten a lot of recognition in the commercial world, right? You pick up the newspaper and you read about driverless cars, and you read about computer Go or computer chess being better than humans and so on. But as I mentioned already, that mathematically we don't have a good description of why deep learning should be working so well. So I want to talk a little bit about what do people do in deep learning, and then at the end of the talk, I'll mention what concerns me mathematically about deep learning. So what do people do in deep learning? First, their choice of sigma. Remember, we want to find a space sigma on which we're going to perform our minimization. So the first aspect of deep learning that is novel is the fact that as the space sigma, they choose the outputs of neural networks. So they don't choose polynomials, they don't choose splines, they don't choose wavelets, rational functions, things that are more familiar to us in approximation theory, in which we studied for 40 or 50 years. They choose neural networks. Well, does everybody in the audience know about neural networks? I don't know, because I can't ask for a raise of hands, but I'm going to assume you probably do, but I'll say some words in case you don't know about neural networks. So I'm going to say some words about what are neural networks, why possibly do they think these things are great. From an approximation theory viewpoint, can we say that neural networks are something special in approximation theory, better than existing technologies we know in approximation? The old stuff, right? The linear and nonlinear approximation of the past? Well, that's what I want to address in the next few slides. So how good are they as a approximation tool, and what's special about them in terms of approximation? And I just did a article for Numerical, a long article where I tried to review what I knew about neural net approximation. There are other reviews that other people have given, but of course I want to advertise mine, which you can look up if you become interested in neural net approximation. So first, some notation. A neural net, maybe I show a graphic first. A neural net, here's what it does. It takes the input X, so it's going to create a function. A neural net, the outputs of a neural net are a function. And how does it create the function? It takes the variable x, which may be a multivariate input. I picture this as R2, that I'm looking to output a function of two variables. And I take the vector x and R2, and I'm going to do certain things to it, and then I'll output my S of x, which is the function I create by the neural network. What do I do? At the first layer, from the input to the first layer, I allow you to take this vector x, apply some matrix A to it, add a bias B, and then I apply something which is called nonlinear activation. Maybe I have it written here. Oh, I don't. Okay, nonlinear activation. So I just don't take ax plus b, but I apply a function to ax plus b. And I'm going to talk mainly about ReLU networks. ReLU networks, the activation function is the x plus function. I should have had this on this slide, but I started messing around with slides for this talk. And well, here it is. The activation is x plus, which means given ax plus b, you truncate it by just taking the positive part of ax plus b, right? If ax plus b is positive, you take that number intact, and if ax plus b is negative, you make it 0. This is important, this nonlinear activation. But this is what you do as you move from input layer to first layer, and every other subsequent layer, you do the same. And then finally, at the last output, you take whatever functions you have here in this last layer at these nodes, and you take a linear combination of them plus a bias, and that is your output. So what is the bottom line? That neural nets create functions, and they create them via matrices and biases. These are the parameters in the neural net. You get to choose the matrix. You get to choose the bias. Given an F, you get to choose them. So the way we look at it is that we fix the depth of the neural network, L, the number of layers. We fix the width, that is how many nodes in a given layer. And we fix the activation. And then when we do this, we get the output of the neural net, the set of outputs. You can stick in any matrices and biases, and you get these outputs. So this class, upsilon WL, represents the outputs of a neural net, which has fixed width W, fixed width L, has ReLU activation defined for functions of n variables. Now, what does this look like? So a good question is, what is the output of a neural network look like? And I want to tell you what it is. This is for ReLU activation. Well, the output of a neural network is going to be a piecewise linear function. Well, okay, so we can at least understand what it is as a function. It's piecewise linear. That is, you take your domain, you divide it into cells, right? Here, cells. The cells are gotten by what we call hyperplane arrangements. In 2 dimensions, it would be given by lines. We would cut the whole space. This is a 2D graphic. So I'd be in R2. I would take R2, and one line, take this line, divides R2 into 2 halves, right? Left half and a right half. And when I take a family of lines, I will get a subdivision of R2 into cells. All right, pictured here. The cells are always convex, good. They're convex. And the function, the output of the neural net is a piecewise linear function on each of these cells. The cells can be infinite. That's why I have this dark gray thing, but a typical cell is this speckled cell here. Okay, so they're piecewise linear functions, but there are some things to understand that I want to bring out. The number of piecewise, okay, so I go back. I'm sorry for jumping around, but I'm going to try to do this in a palatable way without reading through all the technicalities of the slide. If I fix the width and the depth of the network, W and L, the number of parameters I have available to me is like W squared times L. You can check this easily. L is pretty natural, W squared, because I have a matrix of size W times W, right? So this is the number of parameters I have available to me. You should think of this as a dimension, right? W squared times L is the dimension. But the space, the outputs of the neural network are not a linear space. They're a nonlinear parameterized manifold. But with this number right? This number of parameters. An important point is that the number of cells here in the output is humongous compared to the number of parameters. If the number of parameters is n, the number of cells can be exponential in n, 2 to the n, right? It can be huge. All right, so you say, wow, with n parameters, I have a whole lot of functions because I have all these partitions, right? And the number of cells is humongous, and I have no structure to these partitions except that they're convex. So you might think you have a very powerful approximation tool, but there are some caveats to this. Once you prescribe your partition, you do not get every piecewise linear function on this partition. The output of the neural network has dependencies between the linear pieces on these different cells, and this dependency severely restricts the number of outputs of the neural network. So you don't have as much power as you might think. You might think, the way we used to think in spline theory, we can just lay down the partition and then create any piecewise linear on this partition. No, if you lay down the partition, you're very restricted as to the piecewise linear functions you're going to get subordinate to this partition. Okay, I want to, I'm trying to make this part as quick and as easy as possible. Now, let's view of what neural network approximation looks like. In approximation theory, we want to sort of categorize the different methods of approximation. Are they linear? Are they nonlinear? What do they all look like? So neural network approximation, if we want to categorize it, I would categorize it as a form of what we call manifold approximation. So let me explain that to you. In manifold approximation, we're going to approximate our function f by a set sigma n. And sigma n is not a linear space. No. Well, it could be a linear space. But we're going to allow the generality that sigma n is a nonlinear manifold dependent on n parameters. So what do I mean? It means that I have a mapping Mn that given n numbers, it maps me into an element in this case in our Hilbert space. So the sigma n's are functions that depend on n parameters. You might think like rational function, right? Rational function depends on n numbers. Or you might think about a piecewise linear function, which depends on its breakpoints and the coefficients in the piecewise linear function. So but I allow a general manifold. So I'm mapping Mn that maps Rn into sigma n. And neural net approximation, that is these spaces, upsilon WL, are a form of neural network, of manifold approximation. There is a mapping that takes the entries in the matrix, the biases, and uses them to create this piecewise linear function on this very complicated partition. And this is the output. So this is a manifold, right? And now what do we do when we approximate? Given a function f, we look for the parameters, right? We look and say, what parameters should we choose to do the approximation to f? So our game is given f, find the parameters. If you were doing linear approximation, you're finding, you take a basis for your linear space and you're finding the n coefficients with respect to that basis. That's what approximation is, right? In this case, you're finding the n parameters to locate the approximant on the manifold. So the approximation scheme consists of two mappings. One, given f, find the n parameters. Then the second, once you have the n parameters, map it into the manifold. Okay, so a lot to do with manifold approximation is to understand what are you going to allow in terms of these mappings an and mn. If you're too generous and say, well, I'll allow any mapping an and mn, you're going to run into a problem which you're familiar with, namely space-filling manifolds. So suppose I began to study how well can I approximate with manifold approximation. I fix n, the number of parameters in the manifold, and I ask, how well can I approximate a given class of functions, right? Using such a scheme of approximation. Well, the answer is I can approximate it to arbitrary accuracy, right? Arbitrary accuracy. Why? Because there are space-filling manifolds. I can just take my set K and I can give a space-filling curve, even of dimension n equal 1, right? With a one-dimensional manifold, I can generate a space-filling curve that's within epsilon of every element of K, and therefore the error of approximation using this one-dimensional manifold is epsilon, and epsilon is arbitrary. So this concept is useless if you don't put some restrictions on these mappings an and mn back here. Okay. So I claim you have to put some restrictions. In fact, let me. This is I apologize for this is not organized as well as it could be. But let's now go and look at results in neural net approximation. So they're doing a form of manifold approximation, and I caution you, be careful when you evaluate manifold approximation, because you may be entertaining space-filling manifolds, which may sound wonderful, but they're impossible to use numerically, right? If you had a space-filling curve and wanted to use it numerically, how would you find a parameter given f? You would be searching forever to find such a parameter numerically. All right. So what do we know about neural net approximation? Why do people in deep learning use neural nets? Do they have some special approximation properties? And the answer is yes and no. So let me give you the yes part. There are some very surprising results about neural net approximation. And if you take a function and you want to approximate it using neural nets with n parameters, you can achieve an error of approximation that is very surprising. Here is just one of many examples due to Dmitry Yarotsky, who shows that if you take a lip1 function, you can find a ReLU neural network using ReLU activation that approximates the function f to accuracy n to the minus 2. The 2 is the surprising part, right? Because to anybody, I mean, if we use polynomials, splines, anything reasonable that we know, we only get accuracy n to the minus 1, right, for lip1 functions. So this is very surprising, and I call these super convergence results. And there's an array of such results. It's not just for lip1, it's for more general smoothness. So you might say, oh, this is it. This is why they want to use neural net approximation in constructing deep learning algorithms. And I say, hold on a minute, be careful. This is a little bit deceiving. Namely, if you restrict that these mappings AN and MN in neural nets just be continuous, just continuous, already this negates these superconvergence results. You cannot get n to the minus 2. You can only get n to the minus 1. You're back to what we typically agree upon as an optimal performance for lip1. So on the one hand, it looks like neural nets are doing some great job in approximation, but the caveat is that it's the process of generating this approximation is through mappings AN that are very unstable. What does that mean? If I change F a very little bit, the parameters I choose in the neural network change tremendously, right? A very unstable process. And this is part of the answer to a lot of the intriguing questions about neural nets. Okay, so sorry that I didn't do a real good job on this. What I wanted to tell you about neural nets is that it looks like it has some great approximation capacity, but be careful. It has some space filling capacity to it, and this is very unstable. There's actually a known, this instability is known in the literature and is commonly referred to as adversarial learning. And I just bring out this example since it'll be relevant for my last slides. So one of the things you use deep learning and neural nets for is for what are called classification algorithms. In fact, it was just on 60 Minutes yesterday in the United States, they did a thing about face recognition and the fact that face recognition is not so as reliable as you would like to believe, that some guy got arrested as committing a crime through face recognition, and he was not related to the crime at all. So, I mean, there are some problems with these super learning algorithms. So in this classification problem, you're trying to distinguish, in this example here, you have some images and you're trying to understand, is there a certain animal in the image, a pig, or maybe a dog, a cat, or maybe a car or an automobile or airplane, etc. And so you train on data. You receive some data where human beings have said, yes, in this image there is a cat. Yes, in this image there's an airplane. Yes, in this image there's an automobile, etc. And you train the algorithm, and then after you're done training, they observe the following, that they gave the learning algorithm this as data. they gave this pig, this picture of a pig, and they told him this is a pig. And then somebody adds just a very little bit of noise to this original image and gets a new image. This isn't part of the data, it's a new image. And they test their algorithm on this new image, and it gets classified as an airplane. Whereas to our human eyes, it looks like a pig, right? So what's going on? This is part of the instability of the learning algorithm, okay? And maybe I'll bring this out in the last few minutes. So I have 6 minutes, as I understand. Is that right, Volodya?
Yeah, sure.
To say what so this is my reaction to deep learning. This was first, maybe this is my synopsis of why neural net approximation seems to be powerful. I've given some negative part to it, the instability. On the positive end, I should say that for all classical smoothness classes, we can give stable, well, I have to be careful. No, I can't say that. For a lot of classical smoothness classes and the like, there are stable algorithms for neural net approximation. That is, you can restrict the ANs and the MNs to be very nice, even Lipschitz stable mappings. Okay, now deep learning. Let's use the last few minutes to talk about deep learning. So these are things that bother me about deep learning, questions that I think are open, what I think we should concentrate on in order to provide a rigorous theory for deep learning. So as I mentioned, what deep learning does is it uses neural nets as the approximation. One thing that it does not do typically is invoke a specific model class assumption. So we're used to learning theory. Volodya and I worked on this 10 years, 15 years ago. We're used to in learning theory, putting down a model class and then trying to develop a best algorithm given the model class. Typically in deep learning, they don't do this. Now, some defense for why they don't have a model class is perhaps it's in their setting of applications, it's not clear what the model class should be. They're very high dimensional, and it's not so obvious what the model class should be. When you're solving PDEs, it's pretty clear the model class should be a regularity space or smoothness space, but in this setting, it's not. So there's no explicit model class assumption, typically. Well, that bothers me because you can't have a theorem without an explicit model class assumption. People in deep learning would counter this with the following arguments. They would say, yeah, but we use this numerical method of gradient descent, and we put some restrictions on the step size and step direction. And this, in effect, injects an implicit model class assumption. But to me, that bothers me a little bit. I mean, it's like letting the numerical algorithm drive the story. The story should be driven by what do you know about F? What are the model class assumptions? What is the data, et cetera, not from your particular algorithm. I always argued against people who, whenever given a problem, solved it using the same technique they've been using for 25 years. I mean, you should look at the problem fresh and say, what is the best technique? To look at it fresh, you have to invoke a model class assumption. So this bothers me. They do have some theorems on that their method of gradient descent corresponds to some sort of a model class assumption with this neural tangent kernel stuff. I don't want to get into this, too technical to explain here. So I claim this is something that's bothering me, that they don't begin with a model class and then try to prove a theorem. Perhaps they're justified because they don't know what the model class should be, but I still say we should strive for this. And of course, what it means is we need viable model classes in their application domain. What should they be? They should be based on sparsity, or what are high dimensional model classes? Second issue, data. This concerns me a bit. You know, they're solving high dimensional problems, very high dimensional. Let's say, 100 dimension is very modest in their setting. But if I gave you a learning problem in 100 dimensions, even if I gave you 2 to the 100 points, I mean, a humongous number of point evaluations, you would only have 1 point in every quadrant, right, of 100-dimensional space. You would have very coarse resolution. You would have only resolution of order 1/2. So why are you going to be able to learn, you know, in such high dimension with a given data set? Because you'll never have this many data. So this concerns me. Well, it must be that the model class K is very, very stiff. That is, I mean, it's very constrained by its point values. To understand this, we should be computing the Gelfand width of these model classes. So if we think a model class K is good for deep learning, then prove it to me by computing the Gelfand width. Why the Gelfand width? You're not going to do better than the Gelfand width in learning. And if the Gelfand width is not manageable, you'll never have a learning algorithm that is going to perform well. And this is starting to get exposed, and I mentioned these two papers which have gone into showing a gap between how well neural nets approximate and how well they can do from data. There are two different things, right? When you're dealing with approximation, you see the fullness of F. You see F everywhere. When we talk about approximation, we talk about knowing F everywhere. When you talk about learning, you only see the data about F. And the point is that there's a big gap in performance between the approximation and the learning. And it's caused by the fact that the Gelfand width of various model classes is much different than the approximation rate. Okay, computation, something that bothers me in deep learning about computation. We're used to, in numerical analysis, when evaluating an algorithm, to say, well, how long did it take you to compute your approximation? If you're solving PDEs, we know you can solve to arbitrary accuracy if given a long enough time. The question is, how many operations, how much computational energy did you need to achieve a certain error? This is not present, as I see it, in deep learning. They don't count on much computational time. So if you employ a neural net algorithm with some sort of a descent criteria, you may be computing for a month or half a year, 2 years. How do I know how long it's taking you to find this good approximation? Is that fair competition? I think you need to, I argue that computational time should enter the picture. All right, now a few words on stochastic, because everything I did was deterministic, and you can start arguing that, oh, well, you know, he went on and on with all this deterministic stuff, but this is not what we do. We do stochastic, and we have noise, and all that he said is useless. That's not true. And so let me say a few words about the stochastic setting. So in the stochastic setting, you do two things. One is that you have the measurements are random. And that means the sites where you're going to evaluate the function, if you think of point evaluation, you're choosing random sites. That's one aspect of the stochasticity. The other is that you assume you have noisy measurements. And usually those are bundled together in mini-max theorems, right? And they give a result that, okay, given that setting, then the best you can do mini-max estimates in either in expectation or high probability is such and such for the given model class. This was learning theory 10 years ago. I claim you should separate these items. I mean, you should understand what the randomness of the sites is doing, how that's restricting how well you can do, and how the noise is doing. And to bring that out, suppose that I told you that you have random measurements, M random measurements, and you had some classical regularity like S derivatives in RD, and you said, how well can you approximate the function given M random measurements in expectation? You would get a result like big O M to the minus S over D. D is the curse of dimensionality times the log M. The log M is due to the fact you have random sites. You don't have the best sites where to measure. Now, if you look at the minimax estimates, you get a much worse estimation here. You never get past accuracy M to the minus a half, right? Or M to the minus 1 if you square it. That's a big distinction between these two, because if S here is huge, I get better and better approximation. And the reason is that here the noise is dominating. And really you should separate these issues, because if you have a little noise but random measurements, you can do quite well. So I claim this is an issue. Another issue, which I sort of shoved under the rug in the talk, is that if you're talking about doing L2 bounds for approximation and talking about general L2 approximation, you don't have point values for functions in L2, right? Point evaluation is not, is not a linear functional in L2. So how do you get around this? So there the question is, can you incorporate L2 estimates with point evaluation? And I think this is beginning to be understood, and I refer you to Albert and Volodya and their collaborators. Sorry, I don't mention all the collaborators here who are very important. I always hated it when, you know, I was a collaborator, my name wasn't mentioned. I apologize to you. This was done at the last minute here, where I wanted to bring out this point. Understanding why do L2 estimation when the target function, well, you must have model class information that allows it to be point evaluation to be a viable measurement, but it's not a linear functional in L2. So this has to be massaged in some way and is being done. Okay, last slide. This is having to do with classification and what is called adversarial learning. So I assume you know something about this. In classification, if you're doing binary classification, the best classifier is the Bayes classifier. And you're always going to have misclassification near the boundary. So if you take a point near the Bayes boundary and you perturb it a little bit, you'll spill from the region where it's classified as 1 to where it's classified as 0. So you're always going to have tremendous error. You're going to have this pig example. Even though you may have a stable algorithm, you're going to have a problem near the Bayes boundary. So I'm trying to understand what is adversarial. So how are they going to formulate, the problem in adversarial learning? And as I understand it, they would try to understand whether the data they're given is really real data or synthetic data. Did an enemy create the data to fool them, or was it really, or in a real application? And trying to distinguish between the two, and is your algorithm doing okay on real application data and having a problem only with the synthetic adversarial data? Okay, I stopped there. I'm sorry I took a little bit too much time. I apologize. But so I've eaten into question time. Thank you.
Okay, thank you very much, Ron. So now we have time for questions, comments. Are there any? It's hard to tell when you're giving a talk on Zoom whether you're, blowing everybody away. You don't get to see the audience. So yeah, that is.
I apologize if you didn't follow, or maybe you followed and thought it's useless or trivial.
Volodya, may I ask a question?
Sure, go ahead.
So, Ron, what is your best knowledge, the best example of real application for this neural network approximation?
Well, where it's being used is in two applications where it's used often. One is face recognition. So what they're trying to do is, for example, we had in the United States, January, what was it, the 6th, where they went to the Capitol and they were rioting and breaking into the legislative offices. And they have video of that event. And they're trying to find who were these people. Take these video and find out who was that person, match it in some way. And then, so they look on databases which have images and try to match the video image with the database. And this is called face recognition. And so that's one of the applications. So their data is all the existing images that they are given where the people are identified in the images. Another is number identification. The post office, for example, wants to have a reader that reads the envelope where you've written the address of the recipient and wants to know what the numbers are, 13742 Oak Avenue or whatever. And people write differently, right? And sometimes the 1 looks like a 7, the 3 looks like an 8, etc. So they try to have automatic readers, and they have learning algorithms that take the image created by the scanner and try to tell you what the numbers were in the image. So that's two applications. It's used many other ways, by the way, for college admissions. College admissions are now using learning. And this is, I think, rather dangerous because they're very biased learning algorithms. But anyway, that's a long story. Let other people ask other questions.
Thank you, Ron.